This is the last section of our course. Section 6.3, separation of variables and logistic equation. So we already saw that idea of separation of variables. Let's just do one more problem and kind of discuss it. So here, differential equation, y ln x minus xy prime equals to 0. So what is the idea here? The idea is to try to rewrite this, of course using algebraically correct moves, so that the y expressions are on one side and x expressions are on the other. Usually when there are products of x and y, that's a good news. When there is a plus between them, that's not the good news. You say, well, what is minus? I just separate them on different sides. And then what do? I get x is on the left side, y is on the other, so I get ln x over x equals y prime over y. Of course, don't forget that y is a function of x, so it's always there, whether we write it or not. So now I will integrate both sides with respect to x. And that's separation. So when that happens, you can use substitution to integrate this correctly. So what happens here? In this left, in both integration, I use change of variables. So on the left one, what is my substitution? U equals ln x. So du is 1 over x dx. So this will be integral of what? U du equals, on this side I can call maybe y of x, I can call it y, why not? I will call it z, it's less confusing. So then what? When I differentiate, I got y prime of x dx equals d. So this is integral dc over dc. And then we get here y squared over 2, u squared over 2, sorry, equals ln absolute value of z. And then we recall the players, U stands for ln x. C should be somewhere. Where should I put C? Usually where the independent variable is, or wherever that makes it simpler. So I put it on this side. So I'll get what? C plus 1/2 ln x squared equals ln absolute value y of x. We already solved the differential equation. We would rather, if it's possible, whenever it's possible, we would like to solve it explicitly. So what do? We raise both sides to e, so we get what? E. We already know, okay, let me raise it carefully. Equals e to the ln absolute. So what would that give us? E to the c, I don't need that substitution anymore. So I can split that as e to the c times e to the 1/2 ln squared. It's easier when you're ln squared x. E and ln cancel each other out, so I get the absolute value of x. And then I can call this c again, if you want. I can call it a d, but keep in mind that d is positive, like last time. So if absolute value, so I get the following d to the 1/2 ln squared x equals absolute value of x where d is positive. But if absolute value equals to something, then y of x equals plus or minus d to the 1/2 ln squared x. Since d is positive, plus or minus d makes it just arbitrary, so y of x is just d to the 1/2 ln squared of x. What if d is 0? Because that's not justified. This is also not justified if d is positive or negative. But if y of x is 0, then is it satisfied? We get 0 here, y prime is 0, so it's satisfied. So that's also justified just manually. And this is our solution. So nothing really impressive. The same thing. Sometimes give you more complicated calculation, but generally the idea is the same, like problem number 18. as y square root of 1 minus x squared y prime minus x square root of 1 minus y squared equals 0, and y of 0 equals 1. So this time we don't want general solution, we want particular solution containing point 0, 1. So what happens here, the same thing, we split them, y square root of 1 minus x squared y prime equals x square root of 1 minus y squared. Then luckily these are all products, so I can just split them, y prime over square root of 1 minus y squared equals x over square root of 1 minus x. And what now? We recall that this is function of x. Let me emphasize. Like zoom in, zoom out. Zoom in if it's confusing you. So generally what? We integrate with respect to x, both of them. So we get integral of y prime over square root of 1 minus y squared dx of x square root of 1 minus x squared dx. And basically, these are the same integrals, just here, because y is a function, we have chain rule part. Anyway, so the same way, let's see here, call y of x is z, actually not y squared, but not y squared, but even better 1 minus y squared. So 1 minus y squared of x, we'll call that z. And then we get what? Minus 2y of x, y prime of x, dx is dz, so it's derivative ready basically. So this integral here is what? y prime dx, the whole package, is basically minus 1/2 dz over square root of z equals, I'm not going to repeat it, that's the same idea, 1 minus, so it will be what? Integral of minus 1/2 dx over square root of x. No, if I do u, see, when we rush interest, quite lots of dangers to mess it up. So this is u. The same way if I do u substitution, and that would be 1 minus x squared u, then what? Minus 2x dx is du, and I have minus 1/2 du over square root of u. And then what can I do? Get rid of minus 1/2, multiplying by negative 2. And then when I integrate, what happens? Actually, I better leave 1/2, just get rid of minus y. Because they both multiply by negative 1, because then integral 1 over 2 root z is just root z. Equals, and this will be what? Root u plus c. Here it is. Now we recall who is who, so we get what? Square root of 1 minus y squared equals square root of 1 minus x squared plus c. And then, of course, we would like it to look nicer, but I better first fix c so that I get IDP solution. So when we plug x to be 0 and y equals 1, here's what we get. 1 minus 1 is 0, so we get 0 equals 1 plus c. So from here, c is negative 1. So our solution here is this. Now looks like this. Square root of 1 minus y squared equals square root of 1 minus x squared and minus 1. Really, when I plug in x to be 0, y of 0, that's not really right. See, when I plug in 0, no, it is, because 1 minus 0 is 1 minus 1 is 0, so then square root of 1 minus y squared equals 0, so y is plus or minus 1. So generally, this guy will satisfy the equation. So what then, so I would rather simplify this, I'll square both sides. So I get 1 minus y squared equals, when I square this, I get 1 squared first, 1 minus 2 square roots of 1 minus x squared. This is not, sometimes people think that this is the most important. The moment when we get here, we are quite happy with our with our solution. But generally, if you can simplify, that's not a bad thing, of course. So what are we going to do? We'll cancel this one and this one, and then multiply by negative 1. So we get y squared equals x squared plus 2 square root of y minus x squared and minus 1. And then final solution, we can square root it. Y equals, it should be plus or minus the square root. But be careful when x is 0, what will happen when x is 0, we'll get 1 plus, no, it's 0, plus 2 is 2, 2 minus 1 is 1, so we get plus or minus square root of 1. We cannot afford that, so if I put minus, my IVP would be ruined, so I just choose plus, and that's the solution. You see, we were able, even if it was a little more complicated, we were able to solve it. That's you, when you look at my notes, I didn't even finish this last part. I think that it is better if we do this little polishing, especially since we chose the sign, so it's a little nicer. Did I mess it up somewhere? I hope I didn't. It looks good. All right, and then a couple of other types of solving differential equation. One of them is called homogeneous. Those homogeneous equations are the one they could be somewhat unpleasant to integrate. Generally, those are equations that look like this: y prime equals f of x, y. But this expression in f is homogeneous. Formal definition looks like this: f of tx ty equals t to the n. F of x, y. Although in our stories, n will be 0. So basically, let me show you a simpler way, because this needs real algebraic skills. Let me do the example. F of x, y is x cubed plus 3x squared y plus y cubed over x squared plus 3xy. When we calculate homogeneity for rational functions, there is a much simpler way than doing this bad algebra. Not bad, unpleasant. Basically, we count the degree, cumulative degrees for every term. So look at this term. Look at this term. Look at this term. Each of them has cumulative degree 3. So cumulative degree equals 3y, because it has 3 x's as factors. 2 x's and 1 y, that's 3, 3 y is 3. On the bottom, cumulative degree is 2. 2 on x, 1x, 1y, that's 2. So cumulative degree is 3. When you divide by cumulative degree 2, everything will have degree 1. That's the degree, that n. So if you plug in tx, ty, there will be t cubed on top, t squared on the bottom. Altogether, there will be an extra t, and that will make it homogeneous on degree 1. As I said, in differential equations, we usually will do homogeneous of degree 0. So here it is, and let's see how that appears in our calculation. So I'll do one homogeneous equation. I'll tell you how to recognize it and what to do. So example number 38. Y prime equals x squared plus y squared over 2xy. So if you count the degrees, on top every term has degree 2. On the bottom also 2. 2 minus 2 is 0. This is homogeneous with degree 0. So what do you do here? It doesn't separate variables because of this plus. You cannot split x and y on different sides. And then what do? We actually memorize for homogeneous the following substitution. Y equals z times x. So what will happen? So I will still differentiate. So independent was x dependent was y. Now independent will still be x, but dependent will be z. So we want to express everything in terms of z, so that then when we solve for z, of course, we'll multiply it by x and get y. Of course, you say, why should that always help for homogeneous equation? Here's the story. If y equals x, then y prime, using product rule, is z prime x plus zx prime, which is z prime x, x prime is 1 because we are differentiating with respect to x, plus z prime x. So now you remember what we said of substitution. When you do substitution, y disappears completely, z takes over. X is fine. So y prime is z prime x plus z equals, and because of homogeneity, look what will happen. X will disappear on the right side. Z squared x squared, because I replaced y as zx. 2x is zx. And that homogeneity causes that each term has x squared. So we get the following as z prime x plus z equals x squared times 1 plus z squared, or x squared times 2z. This is x squared, this is 2z. So I cancel x squares. And look what happens. X is gone on the right. I still have little troubles with this z, but I'll bring z anyway. That's not a big deal. So I get z prime x is 1 plus z squared over 2z minus this z. I multiply it with 2z up and down to make common denominator. So that's our z from the left. And this will give us 2z. 1 plus z squared minus 2z squared is 1 minus z squared. And what then? Now it separates variables. The z's can go left, x will go right. Everything works perfectly well. So what do we get here? 2z, oops. 2z z prime over 1 minus z squared equals 1 over x. 2z z prime. Now we integrate both sides, which will give us the integral of 2z prime over 1 minus z squared dx, integral 1 over x. Now the right integral is fairly trivial. It's ln x plus c. On the right side, we need some integration substitution. So what would that be? It might be a good idea here to just maybe do that integral along the side. I am tempted here to do it quickly, but I'm not doing it in the box here. Here's the box work. 2z z prime over 1 minus z squared dx equals. We'll say u equals 1 minus z squared. So du is what? Negative 2z z prime. Because it changed. So that 2z z prime dx, everything that we have there, is actually an integral of negative du. So this is integral of a negative du over u, which is minus ln u. When we plug it in, we get minus ln 1 minus z squared. That's great. All right, so now we are ready to enter our result. Here it is. And then, what is the other thing? If I look at it this way, I would definitely prefer to multiply by -1 so that my troubles are more on the right side. So I get the following, ln of absolute value of 1 minus z squared r minus ln x plus c again, because c is arbitrary constant, plus or minus doesn't matter. Now I erase both of them, e to the ln, absolute value of 1 minus z squared is e to the c times e to the minus ln x. And then business as usual, this is absolute value, so I get 1 minus z squared equals plus or minus e to the c times 1 over x.
x, because e to the ln x is 1 over x. Just to make it sure that everybody understands that, e to the minus ln x is e to the ln x to the negative 1. So that's x to the negative 1, which is 1. And then again, plus or minus, e to the c is positive constant with plus or minus, makes it just arbitrary. So we get what? 1 minus e squared equals c over x. Are we done? No, we are not, because we were not solving for z, we were solving for y. So, from here, y over x stands for z. So, when we replace that, we get 1 minus y squared over x squared equals c over x. And then one more move, if I multiply by x squared, I'll make it even nicer. Get x squared minus y squared equals cx. So these would be some hyperbolas with the moving centers. So that's how homogeneous works. So crucial thing is to remember substitution y equals zx. Here's what y prime ends up to be. And then don't forget at the end, of course, to replace that z equals y x. So what happened here? So equation initially was not separable, but then with skillful substitution, it actually became separable. And then one really very interesting equation with lots of good history and application, it's called Logistic Equation. And I'm glad that this is the highlight of our course, because it really, there are interesting stories connected with these equations. It's a logistic equation. And this equation looks like this. dy over dt equals ky times 1 minus y over l. That's absolutely a logistic equation. What happens here? Generally, I think the most valuable part of what we'll do now is that qualitative analysis of what is happening here. So what happens? We are interested. So this is the equation of a population. So we'll just assume that y is greater than or equal to 0. So generally, here's what happens. Let's see what happens if y equals L, if y reaches L for a certain point. So if size of population reaches that number L, that, by the way, is called carrying capacity. Then what happens, if y reaches L, L over L is 1, this factor is 0, so your derivative is 0, that means you don't increase anymore. So that's where, when you get closer to L, generally your increase or decrease completely stops and you stabilize. That one is a horizontal asymptote. So, but what happens then, so if y close to L, dy over dt is close to 0. But if y is close to 0, if you have a very small population, then this is almost 0. 1 minus 0 is close to 1. Then we have something like this. And this is just pure growth. Or decay, depends if k is positive or negative. So basically what happens when you start with a small increase like here. So for example, our population starts here. Then, if it's fairly small, it will increase exponentially, and we know growth goes like this. And it's interesting, we will show that with the calculation. The moment you reach half of your capacity, your function is still being concave up, starts to be concave down, and then it stabilizes along the asymptote. So that's the famous equation of the logistic curve. The same thing. So for example, if I start higher, the same thing. The moment when I reach that level half, it gets an inflection point and goes like this. By the way, what happens, so that's basically like if you have a forest that has capacity for 1,000 inhabitants. Then, if you have 100 inhabitants, there's a natural growth. When they get closer to the capacity, they kind of stabilize and they cannot enjoy the benefits of the forest. What if we have more than capacity is? Then what will happen? Then this will be negative and we'll have just a decay. So it will go like this. So these are the graphs for this equation. It is interesting, Belgian mathematician Verhulst came up with this equation somewhere in the second half of 19th century. And when you apply this equation to the population of the United States, you can see actually that until the Second World War, actually the data calculated by his model they're very close to the real data obtained by the census. And you can see this inflection point happens around Civil War. So it's interesting, and then nowadays we are just not behaving according to this logistic equation, but generally just, this model is not appropriate anymore, but for almost 100 years, it was really very accurate to predict such a dynamic model like population of the United States. Generally, calculationally, so this is more interesting. When you look at it calculationally, this is equation that separates variables. Why? Because there are no t's on the right side. Get y's on the left, integrate, and you can get the formula, and then the formula that appears in pre-calculus books, because they just give them they do integration for them, and they give them the ready-made formulas. So what would that mean? First, I'd like to show, to demonstrate really that why is this inflection point happening exactly at L half. So we'll do the following, we'll just calculate the second derivative. So what, inflection point? So we'll get a second derivative, d2y over dt squared. We'll use the product rule, so it will be k times dy over dt times 1 minus y over L, and plus k times y times what? Negative 1 over L, and then the derivative of y will be dy over dt. And then what would that be? We'll factor out k, we'll factor out dy over dt. So who's left? 1 minus y over L, and minus another y over L. Here's y times 1 over L. Here's y of k is out, dy over dt is out. So if this is 0, unless you are at 0 over on the equilibrium line, so-called, then critical points of the second derivative are here, so that's 1 minus 2y over L equals 0. If you solve 2y over L equals 1, y equals L. So here's where your second derivative is equal to 0, and then what happens before that? So before that, since your first derivative is positive, if you are in between here, this is positive, so you have increase. So this is positive, and then, as I said, if you are between that, this is positive until you reach L half, so you have concave up. So y less than L half, you are concave up. When you exceed L half, this becomes negative, so your function is concave down, as we kind of predicted from qualitative analysis. Let me solve this differential equation to show. We have a formula, because this gives us qualitative analysis, but what if we need to kind of solve specific equation? So we want to solve this. So what we get, we'll just separate and integrate, and that's it. So we'll get what? dy over dt, which is y prime, or ky times 1 minus y over L equals to dt. We'll put the dt here on both sides and integrate. So what do we get here? Integral of dt is just t plus c. What about here? We want to integrate, we'll do substitution y, but generally we need to do the partial fraction decomposition. So there's an easy way to do it. I'll pull out 1 over k, that's not a big deal. I'll multiply by L up and down, so I get Ly prime over y times L minus y dt equals t plus c. And then what? It's very easy to see that this is, I'll get k on the other side, so this is the integral of 1 over y plus 1 over L minus y. I didn't do a over b over, because if you add them up, you see that your L equals kt plus c. So, where's my y prime? Where's my prime? Y prime dt. So if I integrate this, obviously I get ln y minus ln L minus y, which is positive if I'm in between. Minus comes from the linear correction, equals kt plus c. Here I write this as ln the quotient equals kt plus c. Now I raise e to the both sides, and I get the following: e to the ln y over L minus y e to the kt plus c. As usually, a and ln cancel each other out, so I get to y over L minus y equals c e to the kt. And now what do I want? I want to solve for y, so I'll just cross multiply probably, so I get, I'd rather have y multiply. Let me flip them first. Take reciprocals. L minus y over y equals c e to the minus k. That's better. 1 over c, obviously. Now it's better to cross multiply, so I get L minus y is y, c to the minus k. Now we get y on the same side, then I get y, 1 plus c to the minus kt. And when we divide, here it is, we have our solution. Y equals L over 1 plus c to the minus kt. That's the formula that appears in the pre-calculus books. So when t equals 0, when t goes to infinity, you will just get e to the negative infinity 0, so it approaches L over 1, so you approach carrying capacity. And this function is really increasing, and that's it. Now we can describe what C is, why, because let's say that initial population is y0. Then when I plug it in, I get y0 equals L over 1 plus c. So when I solve for c, I get 1 plus c is L over y0. So c is L over y0 minus 1. So generally what? You see how many times capacity increases your start, that ratio minus 1. All right, let's see an example. So now this is ready-made formula. I don't need any differential equations for that. So let's say the following. So here is problem number 76. Solve dy over dt equals 1.2y 1 minus y over 8, and I want y of 0 to be 5. So if you look at our equation, that's exactly a logistic equation, where what your carrying capacity L is 8, denominator here, and what there's our k is 1.2. So generally we'll just plug it in and say y equals 8 over 1 plus. And we actually derived what c should be. the ratio of the, so C in this case would be what? C equals carrying capacity A over your start 5 minus 1, so that's 0.6, 3/5. E to the minus 1.2. Here it is. And then, of course, if you want to polish this, I like to see it like this because then I can read everything I need, you know. So generally, oh, by the way, what happens in this graph? Since you already, so you remember half, so carrying capacity is 8, so inflection point is at 4. Since we started above it, we don't have a inflection point, we are concave down, we slow down from the beginning because we just started at the high value. What I did in my notes, I polished it multiplying by 5, so 40 over 5 plus 3 to the minus 1.2. Right, and it says graph has no inflection point. That's where we finish our section 6.3 and we finish our course math 155, summer 2018. Thank you.